So let's have a look into the 5G technical requirements. After looking into the use cases, the core of the 5G atom, the first tier set with some electrons, with some requests that came really from the use cases. So going from use case to use case, you will find out that all of the use cases would claim that they need massive throughput. They also would tell you that they need resilience and security. Imagine you have a car on a highway without the steering wheel. You would like that the connection to this car is always there, or that nobody from the outside can break in. There are other things like energy that is a side effect that always is important, and heterogeneity, which is a point where you will have to understand if you have billions of devices, you will not have this same kind of devices as we have now. We have different phones like Android and iPhone, but from the device perspective, they are the same. So the network sees them and said, it doesn't matter if it's an iPhone or Android, it's exactly the same for the network. Now, in the future, we will have devices that have no computing power. Some of them have at least a little or a lot of computing power. They have different type of wireless access schemes and data rates available, and how to find solutions that scale instead of making different classes of devices that we mean by heterogeneity. Last but not least, the most important part, as in the IMT 2020 triangle on the right bottom, is latency. Everybody asks about low latency to steer some cyber physical system like cars, trucks, agricultural machines, but also for gaming, latency is something very important. Now, if you go from use case to identify which kind of requests they have for the individuals, then you get some of these spider plots, right? So we looked for the connected cars in something like car control, in-car entertainment, car navigation, predictive maintenance, and then you ask what kind for car control, right? What is it really that we need for computing? Would need a lot of that. Data rate, not so much, but latency is really big because we want to steer and control the cyber physical system. The in-car entertainment needs a lot of data rate, of course, because Netflix and other social networks have to go through here. So even if you just look at the connected cars, there are different fields with different requirements. And the same values are here, but a different plot comes out for the industry 4.0. And if you now block this and say, I would not look into the individual cases within the connected cars, but if I just say this is the area I have to support for the connected cars, then this area is already big. And it's not the same area that you will have for Industry 4.0. If you then look, for example, in farming and smart grids and look at the area they will span, then you will see that there are others like tactile internet, another area that will be spawned here. And if you put them all over each other, like these things, then you will find out that you don't have to understand which use case it is. But if you just block it like this, it's always the maximum of computing, it's always the maximum of data rate, it's always the maximum of latency, etc., etc., etc. So this is tough for a network. And you could do that, but only if you have infinite spectrum available. And spectrum costs money, and therefore we have to understand how to deal with this kind of system. Now, if you just look at data rate, latency, and resilience, this alone is already a problem for a network like this with this given spectrum. So if you look at latency alone, then you could look, why is latency important? And there have been the group of gamers that have always understood this problem of latency. The reason why the gamers met in these big holes is they understood if you would like to have low latency to have this interactive gaming, and you want to have high data rate, the solution is here, proximity. So if you bring them all into one room, everything is fine. But bringing 500 billion devices in one room, that's not fine. So the players always understood latency. They were the only ones since 30 years claiming that latency is important. And there's a nice paper from '96, which is called "It's All About Stupid." It's all about latency, stupid. So a very nice read about latency. Here's a video that comes from TU Munich. Professor Steinbach had this for our excellence cluster. So I took the freedom to show it also here. So what you see is latency between cyber physical systems. And the thing is, you can move one of the joystick on that side, and this movement will be transported with 0 millisecond latency to the other side. And once the second joystick hits the bottom, you will feel it on the other side. That's quite interesting. I just started here for you. So you see that looks very synchronous. If now the network has something like 5 milliseconds, you can see there is a delay, but you will feel something there. Now, what the feeling is hard to say, but if you have already 10 milliseconds, you see how unstable the control loop becomes. That is similar to the behavior of the cars that I have shown you before, right? Good. This is for machines, right? But even humans are sensitive to latency, right? Here, for example, we made a nice goggle, and you see the people should just catch a real ball, right? And in the camera, you see the camera is transporting the real life footage with a little bit of latency. And we here assume we have 40 milliseconds LTE network latency one way. If you go back and forward, it's around 100 milliseconds. And now you see how difficult it is to interoperate in a virtual world with this kind of latency on your neck. Okay, so latency is a problem. The question is, how big can this latency be? So one of the numbers you find in the 3GPP documents is, for example, 1 millisecond. 1 millisecond is very interesting latency end-to-end for smart grids, for example, for human beings. For cars, it could be a little bit larger. But when you think about a sensor and an actuator on the other side, and you want to have this 1 millisecond, then you will see that the 1 millisecond is now paid in different, or the budget for the 1 millisecond is that you have 10% and the sensor together with the embedded computing, another 10% on the actuator with embedded computing. As they are mass market, I think the embedded computing will not be that good. So you lose already 20% on this side. Then for the wireless link, the 5G link, you only have also 20 milliseconds available, because once you leave the base station, you have to go into the wired network. And if we assume the first computing device is 25 kilometers away with the fiber from the base station, then this 25 kilometers will produce more or less twice. It will produce 25% of your milliseconds. And this is interesting because speed of light is way too slow for our examples here. Now, if you calculate, you are remaining here with 35% of your millisecond. And this is that you can enter the virtualized machine and then do some computation here and send it out. And this 35% is not that much, but we come back to that. Why is this so important, the latency? If you understand this 8 of the cars that we have shown in the Nokia demonstration, you see here the cycles, right? And the reason why the cars never crashed is that we made virtually some boundaries around the car. And we made sure that when the car is entering a zone, it will virtually crash with another zone that is empty. Now, if the latency goes up, what you will have to do is you need to increase this kind of security zone. And it's not the mean value that you're interested in, it's also the variance. You have to plan for the worst situation. And if you have a guaranteed latency, that would be the best. So a 3 millisecond guarantee is better than a 1 millisecond mean value with a high variance, for example. So if you now make some measurements there, here for example some latency characteristic of LTE against Wi-Fi, where Wi-Fi there's also 11p for car-to-car communication, the same medium access. You see the latency in milliseconds for LTE is around 30 milliseconds, a little bit higher. This is our local test bed here at the university. And if you increase the number of devices in the intersection, the latency is stable, high but stable. If you look at the Wi-Fi situation, if you have only one device there that you want to communicate with, you can have situations with 1 or 2 milliseconds, but as soon as you increase the number of devices, the latency goes up. That has to do with the medium access, and already after 7 devices, you will have larger delays or mean delays than you will see in the LTE case. So as long as you don't expect more than 7 cars to show up in an intersection, the whole thing will become very complicated. We would like to have something like LTE, but with a given lower latency. And therefore, you need a new air interface to produce these low latencies here. Good. But latency alone is not the problem. If you combine it now with throughput, here are some slides that we derive with our first year students in ComNets, where we say, why don't you plot the theoretical throughput over a packet size, right? And then they can calculate based on the timer information for given OFDM systems, what will be the throughput in byte per second if you increase the packet size, right? Normally you have packets around 1480 here, but you can imagine you can even make them bigger. And the bigger you make the packet, the better is the throughput efficiency on such a system. And on the other side, if you then look at the latency, you see latency will also grow if you build up the MAC segment size. So this is a classical trade-off. You either can have high throughput, but then your delay is not good, or low latency, but then your throughput is not good. And this classical throughput, this classical trade-off between latency and throughput, this is what we have to clean up. If we then think about even resilience, so to make the communication error-free, what you have to apply are things like RQ or FEC schemes. And now this will cause even a negative impact on the latency and on the throughput. Now you have 3 different things that you have to trade off against each other, and you can only optimize for one of them. Here is one plot that we have done for throughput against latency for stop and wait and selective repeat. So these are 2 well-known strategies, and there you see again low latency, low throughput, high latency. Or what you can do are new approaches. This is a new coding scheme where you say, with certain probability, I can have different operating points. Very small delay, even better than stop and wait. But then the throughput is mediocre. Or you can even increase the throughput very high, as high as for selective repeat, but even with lower latency. But still, they might be too high to control a virtual game. So you see there is a trade-off. We can try to beat the trade-off with some new information theory. I will come back to that later. Or there will be something else that I will introduce in a minute. Okay, this brings us to the 5G concepts.